Okay, can you see my screen?
Yes.
Yeah.
Okay, great. So let's start. So last time we talked about the sorting equation and the interpretation of the solution of the sorting equation, namely the wave function. So now we are ready to solve the sorting equation. Okay, so this is what we are going to do today. Solving okay. Oops. Something's wrong with my Apple Pencil. Okay, should be working. Okay, here we go. So solving the sorting equation. Okay, so we have established the framework to how to do quantum mechanics. So the first step is to solve the sorting equation, and the inputs are there are two inputs. The inputs are number one is we need the interaction potential. So just like classical mechanics, if you want to solve the kinetics of a system, then we need to know the force. So same thing in quantum mechanics, the force is described by the potential. So the input, number one input is the potential. Number two is the initial condition, because the sorting equation is a differential equation, and first order in time, if you want to solve that, we need an initial condition. With this tool, we can find out the solution. The solution is a wave function, psi as a function of the space and time. Okay, so that's the first step on how to do quantum mechanics. And after that, so based on our procedures, after we get a wave function, how do we find out the physical quantities of any physical quantities we're interested in? So to do that, we use Born's rule. So basically, by sandwiching the operator you're interested in, like the energy or the momentum, between the wave function like conjugate psi star and psi. Okay? And then we integrate this function over the entire space. Okay, so you're gonna see why this is the case actually in a little bit. Okay, so let's start from the first step. So how do we solve the sorting equation? So let me write down the sorting equation again. So it's I h bar partial t psi equal to the Hamiltonian times psi. The Hamiltonian is minus h bar square over 2m del square plus v of r times psi. Okay, so here you can see we are setting up the sorting equation by letting two ways to represent the total energy systems to be the same. One is by taking the time derivative. Two is by taking the spatial derivative. Then we get the kinetic energy and then plus potential energy. Okay, so if you look at this differential equation again, so the time derivative only involves the first order, and the spatial derivative involves the second order, del square. If it's a one-dimensional system, then this del square simply becomes d squared over dx squared. In fact, for many of the problems we are going to solve initially only applies to one-dimensional. Okay, and later on, for the problems we're really interested in, like the atomic structures and the nuclear structures, and all of them involve the three-dimensional systems. So in that case, we have to expand this del square in three dimensions. So in Cartesian coordinate, del square is a just second derivative with respect to x squared, with respect to x, y, and z. But it's natural for us to use the spherical coordinates to describe like the models of atoms, nuclear. So in that case, so this del square is slightly more complicated. But at any rate, this del square is a function of the space. So either x, y, z or r theta phi. Okay, so right-hand side of the equation does not involve time derivative. Same thing, the left-hand side of the equation does not involve a spatial dependent. Okay, so another quick review is so this equation is a so-called parabolic equation because first order in time and second order in space. And so it's up to the second order, right? So in fact, if you go back to think about all the physics you have learned from classical mechanics, Newton's equations, Lagrange equations, Hamilton's equations, to many of you are plasma students and you have learned like electrodynamics or classical electromagnetism, which is described by the Maxwell's equations, right? So Maxwell's equations is also a differential equation up to the second order. So there we only have up to del square. Okay. And if you well, for all the other students, I think fluid mechanics is also required in our curriculum to think about the differential equation we use to describe the motions of fluids, the so-called Navier-Stokes equation, is also up to the second order, right? So almost all the laws of fundamental laws of physics we have encountered are all described by ordinary or partial differential equations up to the second order. Okay. So second order PDE. And so there are many things in common. Okay. So if you think about what is the meaning of the second order derivative, so the first order derivative means the slope of a curve. And the second order derivative is basically the curvature of the curve. So in fact, nature only cares about these two things, the slope and the curvature. So nature doesn't really care about any of the higher order derivatives. To the derivative to the third order. Okay, so otherwise things will be much more complicated because of the nature we know can be described as second order differential equations and make things a lot of things much easier. So imagine if Newton's law is related to not x double dot, right, or r double dot, the acceleration, but instead it depends on x triple dot or three dots, then all the laws of nature will be much more complicated. Okay, so so mentioned a couple examples of Maxwell's equations, Navier-Stokes equations. In fact, even go beyond that, even general relativity, Einstein's gravity equation is also up to the second order. So most of the laws of physics are described by differential equation up to the second order. Okay, so when we actually try to solve this differential equation, you will see a lot of similarities. So once again, look at this sorting equation. So without the imaginary number I here, okay, it is just a heat equation or diffusion equation. So you must have seen that in your other courses, heat transfer course. So in that case, it's actually almost identical to this. The different equation I'm dealing with is almost identical to this. So let me write it down here. So heat equation is one example. So, in other words, you can, if you come from the background with the heat transfer, you may understand the sorting equation as a heat equation, but with the imaginary time. So we can either write the time as time here, partial t, and then put the imaginary number I there. But you can also absorb this I, this imaginary number, part of the time. So in other words, the sorting equation is a heat equation with imaginary time. So same thing if you comes with from a fluid mechanics background. Okay, so or even more fundamentally, fluid mechanics talks about the motions of atoms or molecules, like in liquid. So in that case, we use a diffusion equation. So here you can also think about this equation, sorting equation, as a diffusion equation, again, along the imaginary time. Okay. So heat equation or diffusion equation. So then in other cases, when the PDE is not the parabolic type, it could be the hyperbolic type. When we want to describe, for example, when we want to describe the classical wave, like electromagnetic waves, or mechanical waves, like sound waves. So in that case, the only difference is that we have to change the left-hand side to second order, right? So when we change this to second order, becomes a wave equation. So that is the classical wave, but again, we don't have the imaginary number I there. So that's the second order PDE. So to solve all of these differential equations, the partial differential equation, what is the general technique? Without knowing much about the details of each differential equations, so the general technique to solve the PDE is to use a method called separation of variables. Right? So let's try to use this method, separation of variables, to solve the sorting equation. So in fact, because of the similarities between sorting equation and the other PDEs that you encounter, the method that we describe here can be applied to the other fields as well. If you have learned them before, this may sound familiar to you. If you haven't, so this is a chance for you to learn this technique, how to solve a partial differential equation. Indeed, in fact, if we talk about specific case, like say this VLFR, it has a certain shape, or in fact, let's say the simplest case would be VLFR equals 0, no interactions. Then we don't have so the right-hand side of this diffusion equation become even simpler, just the del square with some coefficient. Then the solution of this diffusion equation, even the solution of this diffusion equation would resemble some of the solutions in other cases as well. So you can use many of the techniques we described, in fact, in this semester and also in the next semester in 447, but not only to quantum mechanics, but also to all the other problems that are relevant to nuclear engineering, like heat transfer or fluid mechanics. Okay. So again, this is what I mentioned at the beginning of the semester. Besides the physics part of 46, the math part is also very important. Okay, so how do we use the separate variables to solve this differential equation? So the wave function we want to solve is a function of space and time. Okay. Let me write this again. So the wave function psi is a function of space and time. Okay. So in general, if you want to solve this wave function, it could be very complicated. It could be any function of a space and time. And space and time can even be coupled together. So I'm just giving you like arbitrary examples. So the solution could be maybe sine r times t. Okay. So the space and time can be coupled together. So then there are really no easy ways for us to solve this equation. But before going there, what we can do is try to find out a special type of equation. So in a special type of equation, so the spatial dependent part and the time dependent part can be separated out as products. So then we write this down. So space dependent part, we use still psi, but so uncapitalized. So without adding the little bar on top or bottom, we still call this psi as a function of r, and times the time dependent part. So in time dependent part, we call this is the phi as a function of time. Okay, so let's just first try to find out one special type of solutions of the differential equation. And of course, you might be wondering, this solution doesn't include all the possible solutions of the original differential equation, right? Of course, it doesn't. So this special equation, the special form of solution only include the solution where the spatial dependent part can be separate from time dependent part. For example, it could include, just write an arbitrary example. It may be, the dimension may not be right. So let's say it could be like sine, even some like 3r. Of course, this dimension is not right, have to correct the dimension. But let's forget about dimension part. Plus something plus 2, and then times maybe t squared. Okay, this is one type of a solution where the space dependent part and time dependent part can be separated out. So this is included in this special form of a solution. But let's say if we have a sine, still keep 3 here, 3r times t. Okay, so once again, the dimension is not correct. But if we can fix that by putting the correct coefficients with physical quantity, with the physical meanings. So but let's say if this is the case, sine 3rt is the solution, then obviously it's not included in this spatial form, because we cannot write it down in terms of a function of r times a function of t. Okay? But it could still be a solution of the original Schrodinger equation, right? So then you might be confused, but if we try this spatial solution using separate variables, we might be missing a lot of the solutions of the differential equations, right? Okay, so indeed that is correct. So this spatial, that's why it's called the spatial solution, indeed it's not the general solution of the original differential equation. But on the other hand, very soon you'll see, if we can solve this type of solutions, you're able to find out this type of solutions, then the second type, like more general form, can be written as simply as a linear summation of all the possible solutions of the first kind. Okay, so let me give you one example. If you think about a Fourier transform, so you have any arbitrary function. Let me give you one example. So Fourier transform. The Fourier transform, it tells that like any arbitrary curve can be written as a linear summation of all the possible Fourier transform or Fourier series. Transform of Fourier series. So any curve can be written as a summation of Fourier series with sine cosine. So if we want to find out what is the underlying component, then we can decompose this curve in terms of like a sine function with one frequency, and then plus sine functions of even higher frequency. Okay, I'm not very good at drawing that. Let me draw this again. So first, so sine function of a low frequency plus sine functions or even higher frequency. Okay, so when I add these sine curves together, we end up getting the black curve. So each of these individual colored sine functions with certain frequency are like the solutions which the variables can be separated. And overall, the general solution, this black curve, can be written as the summation of different components. Okay, you'll see what I mean actually very soon. So if we so the essence of separate variables is by separating these two variables out, we're able to find out many solutions, not only one solutions. And if we combine all of those solutions where the two variables can be separated, then we can find out the most general solutions. In this case, we're not missing anything. Of course, it still takes a lot of effort of mathematicians to prove that we are not missing a particular kind of a solution. But that is the job of those mathematicians. So for us, we can just carry out this procedure without worrying about losing any solutions. Okay, so let's use the separation of variables to solve our sorting equation. So we write down the wave function in terms of spatial dependent part, time dependent part. Let's put this back to the sorting equation. Then we have a IH bar. Now the partial derivative with respect to time. In fact, let me write it down here for now. So psi the function of r, phi as the function of t. So let's still just simply plug this psi back to the differential to the sorting equation. And right hand side becomes minus bar square over 2m. So del square, so del square, it's the space dependent part, and the plus v of r space dependent part. So this applies to psi r and phi t. Okay. So now what do we do? So in the method of separate variables, the solution is now separated into space dependent part and time dependent part. Now we put it back to differential equation. Then we rearrange the equation so that one side of the equation only depends on the space, the other side only depends on time. So, so the left hand side, so psi r now can be taken out. So this IH bar, partial t will becomes d dt times the right here. So the partial derivative partial become d, so d phi dt, and then times the psi r. Okay, so the right hand side is the same. V of r. Okay, remember what I wrote in here. Inside the angular bracket is a differential operator, so that operates on psi r. So after that, we times the time dependent part, because the operator doesn't have any time dependence. So we can take away the psi t out. Okay, so now we move. Let's say we move the time dependent part to the left hand side of the equation. And here, let's move the spatial dependent part to the right hand side of the equation. So now we have IH bar 1 over phi t and d phi t over dt equal to, so the right hand side becomes so 1 over one. Oops. 1 over psi r and times the whole thing minus bar square over 2m del square plus v of r in operating on this psi r. Okay, so simply divide both sides by psi r and phi t. Okay. So now we still have the differential equations, but this is much simpler than the original form, because the left hand side So left-hand side of equation only depend on time, and right-hand side of equation only depend on space. So in general, for any phi of t or psi of r, so if you plug it in, so left-hand side will give you a function as a function of time, and right-hand side will be a function as a function of r. But we want this equation to be satisfied at any time and any space r. Right? So the only way for this to happen is both sides do not depend on those variables anymore. Right? So the left-hand side will become a constant. Same thing with the right-hand side. So otherwise, let's say if the left-hand side is still contains t. So let's say this t, let's say a simple function of t, like maybe t squared. Then the value will depend on actual time. It won't be always the same to the right-hand side as a function of r. The same argument can be made the other way around. So if the right-hand side is a function of r, let's say 3r, then depending on where you look at the space, and the left-hand side cannot be always the same. So the only way for these differential equations to be satisfied all the time is that both of them need to sacrifice. So they don't depend on their variables anymore. They only depend on constant. So let's call this constant to be E. Okay. So why do we call that E? Oh, this is more like an afterthought. So later on, you'll see this constant indeed is the energy of the system. Okay. So but for now, let's just treat E as a constant. So if it's constant, then we have two different equations. So the first one is the time-dependent part. It is I h bar 1 over phi. We can write down as phi of t, but for simplicity, let's just drop the t dependence, but you can write it down there if you want. So this is equal to E. So this is the left-hand side of the equation. And of course, the right-hand side of the equation is there as well. But let's take a look at the left-hand side first. So this is the left-hand side of the equation. Now it is a first-order ODE. I think it's a very, very simple first-order ODE. It's linear. So we can solve this differential equation. So how do we solve this ODE? So again, it's kind of like the idea of separable variables. So we keep the phi-dependent part on one side. So left-hand side is d phi over phi. And let's move everything to the right-hand side. The right-hand side becomes dt, so times dt. And we have E here, have E and divided by h bar, and divided by I to become minus I. Okay. So then we integrate both sides. So we integrate both sides, and so to integrate both sides, E over h bar dt. We get left-hand side is log of phi, and right-hand side is just linear minus I E over h bar times t. Okay, so what is the solution? The solution phi will be exponential minus I E over h bar t. Okay, so if you want to know, just put this phi dependence, time dependence here. So phi of t is very simple. It's an exponential function. Okay. So now we're able to find a part of the solution of the Schrodinger equation, time dependence part. So you may say, wait a minute, we didn't even use any interactions, right? And indeed, that is true. So when we use the separate variables, we separate time-dependent part from the space-dependent part. And only the space-dependent part that depends on the interaction we offer. And the reason we can separate the two is exactly because of going back to the original Schrodinger equation. Here, see this potential part doesn't depend on time. So this is not V a function of R and T. This interaction we're dealing with do not depend on T. Otherwise, we cannot easily separate these two anymore. The solution would depend on the exact interaction. But the interactions we deal with let's say the Coulomb interaction between the hydrogen inside the hydrogen atom between the proton and the electron doesn't depend on time. And the nuclear interactions between the neutron proton doesn't depend on time. Okay? So in fact, many of the interactions we deal with doesn't depend on time. So that is why, without knowing the detailed features of the interaction, we can already solve the time-dependent part. So phi of t is nothing but a simple exponential form. Okay. Now, how about the space-dependent part? The space-dependent part is minus h bar squared over 2m del squared plus v of r, okay, times the psi r. So now let's move this psi r to the right-hand side again. So this is equal to E times psi r. Okay. So this is the time-dependent part of the sorting equation. It's simpler than the original differential equation because there's no time dependence anymore, right? And can we keep solving that? Well, that would really need this interaction potential V of R. So in fact, this is indeed called the time independent sorting equation. Okay, so as the name says, this is a sorting equation, but no time dependent. So whereas time dependency in this box just above it, so phi of t is e to the it's a simple form of e to the it's an exponential function of the energy. Okay. So then what is the general solution? So this psi is separate this special solution. Special will be equal to the space-dependent part, which is yet to be solved for any individual problem because it depends on the interaction V. And then times the time-dependent part. And time-dependent part can be solved separately. In general, the solution is a simple exponential function. Okay, so this is the solution. It's a special solution of the sorting equation, where the space-dependent part and time-dependent part can be separated out. So because the time-dependent part doesn't depend on the detailed actions, then we only need to do this one time. So in the future, when you need to solve the sorting equation for different problems, you don't have to do the separate variables like here again, because you always do the same. It doesn't depend on the V of R. So that's why oftentimes we don't do it. You'll be only asked to do this one time, okay, maybe 2 times in your homework or in your exams. But in the future, you don't have to do this anymore. So the only thing we need to do is to solve this time independent sorting equation. Okay. So if you look at this time independent sorting equation again, so what is the left-hand side of the equation? It's a minus h bar squared 2m del squared plus V of R. So that is exactly the Hamiltonian. So the Hamiltonian of the system, Hamiltonian operator, V of R, is exactly the left-hand side of the equation. So in other words, this time-independent sorting equation can also be written as h times psi r is equal to E times psi r, right? So in fact, let's make it even simpler. Let's drop the R dependence. Let's drop the R. Let's keep in mind this wave function psi is a function of the space. So h psi is equal to E psi. And h is the Hamiltonian in quantum mechanics. It is operator. So we add a hat to indicate it's an operator. Okay. So now the time independent sorting equation can be written as simple as h psi times E psi. Okay. So, so this equation, this type of equation, an operator times something is equal to a constant times something. The same thing. It's called the eigen equation, where this constant is called the eigenvalue, and these two, the function or the solution is called the eigenfunction. Okay, so time, in other words, the time-independent Schrodinger equation is nothing but the eigenequation of the Hamiltonian. Okay, and this is the equation we solve all the time. So given the entire potential V of R, then we know the Hamiltonian, operator, then we solve the eigenequation of the Hamiltonian and find out the solution. The solution will be the eigenequation, the eigenfunction. In fact, we're gonna have two components in the solution. One of them is this eigenfunction. But at the same time, we're able to find out eigenfunction. We also get the eigenvalues out. Okay. So if you know a little bit of linear algebra, so you can consider this operator as a matrix. Let's say if it's 3 by 3 matrix, and for matrix, then you can solve the eigenvalues and eigenvectors of that matrix. Right? So this is in fact that is exactly the same thing here. And for the graduate students in 521, in fact, we are indeed going to write down this operator in terms of matrices. It's a matrix representation of the operators. Then solving this eigenequation is exactly like solving the eigenvalues and eigenvectors for the matrices. Okay. So another comment I want to make is in some more advanced quantum mechanics, this is the starting point of quantum mechanics. So we can describe quantum mechanics in a much more formal way. So in that case, we don't have to start from the Schrodinger equation. And many of the equations we solve are the eigenequations of differential operators of different quantities. So it's just oftentimes we're interested in energy, so we start by solving the energy or Hamiltonian eigenequations. But if we are interested in the momentum or angular momentum of the system, we don't have to go back to the Schrodinger equation. We can directly solve eigenequation of the quantity you're interested in. Okay. So what appears as a consequence of sequential variables is indeed much more general. So for now, you don't have to worry about it too much. Just remember, we start from the Schrodinger equation, separate the variables, and then at the end of the day, for every single system, we need to solve this Hamiltonian eigenequation or the time-independent Schrodinger equation. Okay, so when you do that, in fact, if you solve this eigenequation, it is still a differential equation because Hamiltonian has a differential operator del square. It could be partial differential equation if we're thinking about more than one dimension, like 3 dimension. Del square will be partial derivative. If it's a one-dimensional system, its del square becomes d square over dx square. And V of R, of course, becomes Vx. So one-dimensional system becomes an ODE. So this differential equation can be both ODE, ordinary differential equations, or PDE's partial differential equation. And the solutions are not, we have multiple solutions. Right? So the solution not only one eigenfunction or eigenvalue. So the solution of this eigenequation is a set of En and psi n. So I added a sub index here. N can be is integer 0 to infinity. So when we solve this eigenequation, we get E0 corresponding to the eigenfunction psi 0 and E1 psi 1. So it's a set of solutions. Okay. So then after that, we still want to know the most general form of a solution of the Schrodinger equation. Right? So we still want to know psi as a function of R and T. So how do we construct that? Then if we know the individual solutions where the variables can be separated, just like the one I wrote here. Okay, so then, so psi r of t, so psi r, psi n times e to the minus I over h bar e n t is one solution of the differential equation, and this one solution can be separated out. So space-dependent part times the time-dependent part. So if you know all of them, all the sides of En and psi n, which can be obtained by solving the above eigenequation, then the mathematicians told us the most general form of the solution is just the linear summation. So here Cn are constant. So it's linear summation of all the possible solutions. Okay, so this is sum over this index n. So when we are able to solve individual separable solutions, then we can construct the most general form of the solution by just simply add them up. Then we're not losing anything. Okay? So that includes even the solutions where the R and T cannot be separated. Okay. So this is the most general form of the solution. Going back to think about the procedure, how do we get that? So with the separation of variables, okay, right here. So we use a separation variable to separate the two space-dependent part times the time-dependent part. And phi of t can be solved in general. It's an exponential function. And the psi r will depend on the interaction or the potential. And by solving this time-independent sorting equation for every individual systems, I'm going to give you one example in the recorded lecture for the square wave potential. Then you see we're able to solve many ENs and phi n. Then by putting all the different pieces together, we finally find out the most general solutions of the differential equation. It's the sum, the linear summation of the separable solutions. Okay. Then there's one more thing left, right? So we still need to know what those coefficients are, the Cn. Without those, we still do not have the final form. So those Cn's are determined by the initial conditions. So we haven't used the initial conditions yet, right? So solving the phi n, the phi n space-dependent part will depend on interaction potential VL part. That's one input of the Schrodinger equation. The other input we need is the initial condition. So this is where the initial conditions come from. So we need to know at time zero, right here, what is the wave function? Say R of 0. If we do not know that, then obviously we cannot find out all these prefacts. Usually in classical mechanics, if we don't know at time 0 what particle is, then of course we cannot predict its long time behavior. So this psi RT at equal to 0 is something I need to give you so that you can find out the Cn. So if we know this psi RT t equal to 0, then we'll put it back in here, so we get sum over Cn psi n of r. Right? So when t equal to 0, then exponential form becomes 1. Okay. So now how do we find out Cn here? So psi R0 is known. So Cn would be like the different components inside this function of R, which projects to this psi n R. Okay, so Cn with this, Cn will be equal to integral of psi R of 0 times psi n star R in D3R. Okay, so this will require a little bit more time to explain. So let me write it here. In fact, it's much simpler if we take a look at the example. And this is the example I'm going to record and share with you on Friday. So, but very quickly to give an idea why we can do this, you can, going back to think about linear algebra, you can think about each of these psi n, psi 1 as a function of R, psi 2 as a function of R, is a linear space. And psi RT at t equals 0 is one vector in this space. And the so-called C1, C2, C3 are just the projection of this vector onto these different axes. Okay. So if you do inner product between RT, R0 to the unit axis, then we'll be able to find out the C1, C2. So this is from a linear algebra perspective. And from a Fourier transform analysis perspective, then each of the psi n will be a sine cosine function. If this is our sine cosine function, then the Cn's will be the Fourier coefficients of this Fourier series. Okay, so we can also do the expansion and find out Cn. Okay, so there are more rigorous ways that we can write this down and explain that, but that is it's not very hard. It may take maybe another hour also to explain, but it's much easier if we take a look at the example first. Okay, so to summarize, how do we solve the Schrodinger equation? We use the separate variables, but even can forget about that part because we don't have to do that all the time. How do we solve the Schrodinger equation comes down to solve the time-independent Schrodinger equation. So the only thing we have to repeat every time is to solve this time-independent Schrodinger equation. And after that, we simply write down the general solutions this way because the time-dependent part is already done. Okay, and then we use the initial condition to match the coefficient. So that's it. So we only need to solve is the time-independent Schrodinger equation, or the Hamiltonian, the eigenequation of the Hamiltonian. Okay. So this is the general framework. Of course, a little bit abstract, but it'll be much clearer when I show you one example. The one example I'm going to show is one-dimensional. So the space-dependent part only become d dx squared, and the simple square wave potential. Okay. So let me stop sharing. Okay. Let's stop recording.